Hello everyone, I'm HyunJae from Lunit. Today, I would like to share our work improving multi-fidelity optimization with a recurring learning rate for hyperparameter tuning. Despite the huge success of deep learning, the performance of CNNs is greatly affected by the choice of hyperparameters. To give you a general picture of HPO, let's suppose that we have data and deep neural network to train. In order to train a network, we need to adjust a set of hyperparameter configurations. In practice, we try numerous set of configurations to push the performance of the network. Then how can we try these configurations more efficiently? Let's suppose that we have run various configurations and we have got the intermediate performances as shown in the figure. Do we need to run all the experiments to find the best one? We do not need to run them all, as it will unnecessarily charge you wasted resources. Multi-fidelity optimization tries to save resources by early stopping unpromising experiments. The most common algorithm is called successive halving. We train all configurations until the initial budget is spent and keep only top 50%. Then we double the budget and repeat this process until only one configuration is left. Successive halving has an assumption that trials that perform well at the earlier epochs also perform well at the end. However, we experimentally found out that this assumption doesn't apply when training CNNs. In this case, successive halving will result in discarding high-performing configurations. In order to mitigate this problem, we have proposed multi-fidelity optimization with recurring learning rate algorithm that condenses the learning rate schedule to fit into every round of promotion, then applies successive halving. MORL first suggests a set of hyperparameter configurations, then it initializes the network for each hyperparameter. On each round, the beginning and the last epoch is computed, and each configuration is trained following cosine annealing learning rate schedule within each round. Every hyperparameter is evaluated after training with allocated resources, and top 1/eta configurations are promoted, and resource increases by a factor of eta on each round. And by adopting MORL, we were able to let the best configuration consistently show a prominent ranking at the end of each cycle, which leads to better multi-fidelity optimization. In object classification task, MORL significantly outperforms other methods throughout the optimization process. Our method consistently works well across varying datasets and achieves relatively narrow confidence interval. In addition, MORL improves the performance of baseline with a meaningful margin in all tested networks. Furthermore, in semi-supervised learning task, our method significantly boosts the performance without the warm-up stage. MORL and Bayesian optimization complement each other by exploring more configurations and adaptively suggesting configurations. And finally, the effectiveness of MORL is not constrained to a certain learning rate schedule. Thank you for listening.